Today we're going to be talking about the graphs of other trig functions. Previously, we talked about the graphs of both sine and cosine. Today, we're going to talk about the graphs of tangent, cotangent, secant, and cosecant. Now, to start off, let's talk a little bit about tangent. When we're looking at tangent, we've stated previously that tangent is sine over cosine. This was the quotient property. Now, because tangent is a combination of both sine and cosine, and we have a denominator here, tangent is going to behave differently than both sine and cosine. So sine and cosine were always defined for every possible angle because sine had a domain of all reals. Similarly, cosine had a domain of all reals, but a range between -1 and 1. Tangent, however, because it's divided by cosine, and we have the rule that you can't divide by 0, every time cosine is 0, our graph is going to be undefined. So, since our graph is going to be undefined everywhere that cosine is 0, this is going to occur, if we look at the unit circle, anytime we are at either 90 degrees or 270 degrees, or in radians, pi over 2 or 3 pi over 2. Now, this is in the first cycle, but again, with all trig functions, we can repeatedly go around and follow this same pattern. So it's any time where we are equivalent to pi over 2 or 3 pi over 2, because these are when the x value is 0. So every time we have one of these, we're going to have a vertical asymptote because this cannot cancel. So if we look at a basic graph of tangent, we're going to have vertical asymptotes at pi over 2 and at 3 pi over 2. And all the other points within the first cycle are going to be fine. So in the beginning, at the first quadrantal, our x value is 1 and our y value is 0. That means at this point, our graph is actually going to be at the origin. But what's going to happen is as we approach pi over 2, our x value is going to get very, very, very small, and our y value is going to get close to 1. As we have a y value, so our numerator is 1, and our denominator is very, 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 very small, we're going to get a very big number. And so that means when we have this vertical asymptote that is going through pi over 2, so as we approach this vertical asymptote at pi over 2, our graph is going to be approaching positive infinity because, again, the y value is going to be close to 1, but the x value, or the denominator, is going to be super, super small. And as it gets smaller, our total value gets bigger and bigger. Now, as soon as we cross pi over 2, we're going to have a very similar issue where our values for x are very, very small and our value for y is 1, but our x values that are very small are now negative because they're now to the left of the y-axis. And so just to the right of pi over 2, we're going to be approaching negative infinity. Now, at pi, our y value is going to be 0 and our x value is going to be -1, meaning that we're going to go, again, at the x-axis. So that means between here and here, we're going to be approaching negative infinity. And this pattern is going to repeat as we go through, and we find that as we go towards 3 pi over 2, which is another vertical asymptote because our x value is 0, we're going to be approaching from the left positive infinity and from the right negative infinity. And so we end up getting this repeated pattern. And so the pattern here, we go from negative infinity through 0 and then up to positive infinity. Now, because this pattern repeats every pi, so this is pi over 2, this is 3 pi over 2, this is one full cycle, essentially the period of tangent, instead of being 2 pi, aka going around the full unit circle, the period is actually going to be pi. And the reason for this, again, is because we're cycling as we do half of the unit circle. So as we do the fourth and first quadrant, our x values are going to be positive, and our y values are going to be both negative and positive, but we're going to be approaching the y-axis. And this y-axis, when we cross this, that's when x is 0. And because x is 0, we know that both of these points are going to be vertical asymptotes. So we're going to have one cycle between the fourth and first quadrant, and then we're going to have another cycle between the second and third quadrant. So the pattern repeats twice as we go around the unit circle. Cotangent is going to behave very similarly, but instead of sine over cosine, cotangent is the reciprocal function, cosine over sine. So sine is 0 at 0 and at pi. So that's when the y value is 0. So our vertical asymptotes here, instead of being at pi over 2 and 3 pi over 2, now our vertical asymptotes are going to occur at 0, pi, 2 pi, and any repeated cycle of this. So now we're going to have a vertical asymptote on the axis here, and we're going to have another vertical asymptote at pi, and another one at 2 pi, and one at negative pi, so forth and so on, because these are the times when we go around the unit circle that our y value is 0. These are the spots where we are on the x-axis. So the other key features that we want to talk about is what happens at pi over 2 and 3 pi over 2. Well, at pi over 2, our x value is 0, so our numerator is 0, and our denominator is 1. So that means we're going to be at the point 0. And at 3 pi over 2, similarly, our numerator is going to be 0, and our denominator is going to be negative 1. Now, with tangent, we went and we approached negative infinity when we're just to the right of our vertical asymptote, and positive infinity when we are just to the left. Well, here, when we are just above the angle 0, so slightly above this, our y value is going to be very small, and our x value is going to be 1. So we're going to have 1 divided by something very small. So that means we're going to be approaching positive infinity. So that means as we approach to the right of these vertical asymptotes, we're going to be approaching positive infinity. And when we come to the left of the vertical asymptote, now our x value is going to be negative 1, and our y value is very small, so we're going to be approaching negative infinity. And so we're going to get the same pattern we had with tangent, except for now it's flipped. So instead of going from left to right, going from negative infinity to positive infinity, now we're going to go from positive infinity to negative infinity. And instead of starting our pattern at negative pi over 2 and ending at pi over 2, or starting at pi over 2 and ending at 3 pi over 2, instead, we're going to start at 0 and end at pi. And we're going to go from pi to 2 pi. So it's as if you took the tangent function and flipped it upside down. So where we would be approaching negative infinity for a tangent, we're going to be approaching positive infinity and vice versa. But it's also shifted over because our vertical asymptotes are shifted 90 degrees off from where they were in tangent. Because now instead of looking at when our x's are 0, we're now looking at where our y's are 0. And so that changes where our vertical asymptotes are. So for tangent, our vertical asymptotes were every time cosine was 0. But for cotangent, it's every time sine is 0. And so this difference means that our graphs are going to be essentially shifted versions and reflected versions. Now, if we wanted to look at the graph of secant, secant is the reciprocal of cosine. So this is 1 over cosine. And so again, because we have cosine in the denominator, we're going to have vertical asymptotes. So we're going to have vertical asymptotes at all the points that we had vertical asymptotes in the tangent function. So if we look at our standard pi over 2, pi, 3 pi over 2, and 2 pi, and we look at this cycle, we can do it both positive and negative. So when we look at this, everywhere that our x value is 0, which is at pi over 2 or 90, and 3 pi over 2, we're going to have vertical asymptotes. So we're going to have vertical asymptotes here, and at 3 pi over 2, and at negative pi over 2. Because again, negative pi over 2 is the same as 3 pi over 2, but we just go, instead of going counterclockwise like we do normally, we're going to go clockwise around the circle. And then at negative 3 pi over 2. So let's talk about how to graph secant. So we know we have these vertical asymptotes that are pi apart, starting at pi over 2. But when we're approaching this first one of pi over 2, our x values are very small, but they are positive. And so that means we're going to be approaching positive infinity. So as we get here, we're going to be going towards positive infinity. Okay. But since our numerator is always going to be 1, and our values for cosine are always between, again, for cosine, the values or the range is between -1 and 1. So we're dividing 1 by, at its smallest, -1. So 1 divided by -1 is -1. And at its largest, 1 divided by 1 is 1. So since we're dividing by something smaller or in between -1 and 1, 1 divided by something that is equal to or smaller than 1 is always going to be 1 or larger. And so what I mean by that is if we look at this first point that we could plug in 0, the cosine of 0 is 1, and so we're going to get 1 divided by 1. So that means at the 0 point, we're going to get a point here at 1. So if this is 1 and this is -1, we're going to get +1 here because 1 divided by 1. And then as we approach this asymptote, we're going to be going to positive infinity. Again, because our x value is always going to be positive when we're to the left of pi over 2 or in the first quadrant here, our x value is positive. So when we get these really, really small values for x, we're getting 1 divided by a really, really small positive value. So we're going to go to positive infinity. And when we look at pi, so over here, our x value is -1, so 1 divided by -1. So we're going to get a point right down here. So let me write my pi over here. So we're going to get a point at -1. And when we are approaching our vertical asymptote at pi over 2, our x values are negative. So it's 1 divided by a really small negative number. So we're going to be approaching the right side of this asymptote at negative infinity. And when we approach 3 pi over 2, we're also going to be approaching at negative infinity because our x values are still negative. So what we end up getting is we end up getting this parabola that goes between negative infinity and negative infinity in between pi over 2 and 3 pi over 2. And if we go backwards here, when we go towards negative pi over 2 in the fourth quadrant, aka moving to the left here, our x values are still going to be positive. So this is similarly going to be approaching positive infinity. So we end up getting this pattern of parabolas that are restricted in between our vertical asymptotes and that alternate between both of them going to positive infinity and both of them going to negative infinity. Now, the interesting thing about this pattern is how it relates to cosine. So if we were to plot the graph of cosine, cosine starts at 1, then at pi over 2 it goes to 0, then it goes to negative 1 at pi, then it goes back to 0 at 3 pi over 2, and then it goes back to positive 1 at 2 pi. So if we look at the pattern of cosine, or the wave pattern of cosine compared to secant, is essentially all of the u or parabolas that we end up forming touch at those quadrantals and they match perfectly where they would be for cosine. So again, cosine starts at R1 and then goes to 0 and then negative 1 and then goes back to positive 1. Well, all the points that were at 1 or negative 1, that's where our secant is at 1 or negative 1. And then if it was at positive 1, then we're going to go to positive infinity as we approach the vertical asymptotes. If we're at negative 1, then our graph's going to go to negative infinity on both sides. Now, the last graph that I want to talk about is that of cosecant. So cosecant is 1 over sine x. And since it's 1 over sine x, we're going to have a similar pattern to cotangent in terms of our vertical asymptotes. So our vertical asymptotes are going to be at the y-axis. And instead of at pi over 2, like with secant, we're going to have it at pi, 2 pi, 3 pi, negative pi, and any multiple of pi. And so we're going to have these vertical asymptotes. And similarly to secant, if we look at our key points, so at 0, this is undefined. So we have a vertical asymptote at x equals 0. But if we look at pi over 2, our y value is at 1. So we're going to have 1 divided by 1. So that means we're going to have this point here. And similarly to secant, as we approach our vertical asymptotes, either to the left or to the right, we're going to be going, in this case, to positive infinity. Because in the first and second quadrant, our y values are always positive. So 1 divided by a positive number is always going to be positive. So our parabola here is going to be jammed in between these two vertical asymptotes, and it's going to have a vertex at 1. Similarly, when we look at 3 pi over 2, so we're going to have the point -1, because again, at 3 pi over 2, our y value is -1, and 1 divided by -1 is going to be -1. And here we're going to have our parabola with a vertex of -1 going through and approaching our vertical asymptotes on either side. And we're going to have a similar pattern here. And similarly over here. So just like with secant, if we were to look at the graph of sine, sine starts at 0, then goes to 1 at pi over 2, then it goes to 0 at pi, then it goes to -1 at 3 pi over 2, and back to 0 at 2 pi. So if we were to graph this sine function, you'll notice that the graph here touches all the points or all the vertexes of these parabolas. Now, for tangent and cotangent, both of these had a period of pi. So, period of pi, because the cycle repeated twice as often. So, we have a full cycle between 0 and pi here, and between -pi over 2 and pi over 2 here. But with secant, because we cycle between a parabola going to positive infinity and negative infinity, a full cycle does take 2 pi. So the full cycle of secant, if we were to start at 0, goes up to positive infinity, down to negative infinity, to -1, to negative infinity, to positive infinity, and back to 1. So that cycle took place between 0 and 2 pi. Or if we want, we can look at it from -pi over 2 to 3 pi over 2. But either way, we're getting this repeated pattern. And a full cycle includes both a parabola going to the positive infinities on both sides and the negative infinities on both sides. So our period for these is similar to sine and cosine. It is 2 pi. Cosecant, similarly, we have to include both the negative parabolas and the positive parabolas. So here we also have a period of 2 pi. Now, a couple of other key things to notice for all of these is if we look at the domain. So the domain of tangent is going to be all real numbers such that cosine of x does not equal 0. So those are multiples of, again, pi over 2. And so the way you'd write that is you'd say n times pi over 2. So for example, if n was -5, -5 pi over 2 is going to be a vertical asymptote. If you set n to 3, 3 pi over 2 is going to be a vertical asymptote. If you set it to 7, 7 pi over 2 is going to be a vertical asymptote. So for cotangent, it's every multiple of pi. So again, the domain is all reals such that sine of x does not equal 0. And so this pattern occurs every pi. So n times pi and 0, where again n is an integer. Similarly, secant and cosecant are going to follow the exact same patterns because secant we're dividing by cosine of x. Our domain is going to be all reals such that cosine of x cannot equal 0. And so that's going to be multiples of pi over 2, n times pi over 2. And for cosecant, because it's dividing by sine, our domain is going to be all reals such that sine of x does not equal 0. And so that's 0 and multiples of n times pi, where n is an integer. If we look at the domain and range of cosine and sine, so for sine, the domain is unrestricted. It is all real numbers. Any angle can be plugged in. Similarly for cosine, our domain is all reals. But our range for sine and cosine, so range was between -1 and 1, including the points -1 and 1. However, for tangent, our range is actually going to be all reals, or from the way we would actually write this is, so it's going to be from -infinity to infinity. And that's because we approach, as we go to these vertical asymptotes, we approach both positive and negative infinity. And the same is going to be true for cotangent. So all of them have an infinite wide range, but their domain is restricted. Whereas for sine and cosine, their domain is infinitely large, it's all reals, but their range is severely restricted between -1 and 1. So if we look at tangent and cotangent, we smoothly go through all the points. For secant and cosecant, though, we actually do have a slightly different range restriction, because although we do go to -infinity and positive infinity, just like tangent and cotangent, we actually can never get to a value of 0, because 1 divided by something can never be 0. So we actually do have restrictions. So our range here is going to be from -infinity to -1, including -1, and from 1, so union, and from 1 to positive infinity. And the reason for that is, again, our values can never fall in between these -1 and 1, because since we're dividing by cosine and the biggest value for cosine is going to be 1, 1 divided by 1 is 1. So in terms of positive values, we can't get a fraction less than 1. So 1 divided by something smaller than 1 is never going to be less than 1. So cosine can never be bigger than our numerator. And so we can't have values between 0 and 1, excluding the value of 1. We can have the value 1 because cosine of 0 is 1, and 1 divided by 1 is 1. And similarly, for the negative values, we can't have values between 0 and -1 because, or by the same logic. So the values for cosine are never going to be greater than -1. And so we're never going to have a fraction for secant that's between -1 and 1. Those are essentially restricted or limited. For cosecant, it's the same thing. So our range, we can do all of the values that are negative, that are less than -1, and we can do all the values that are positive, that are greater than 1, but any of the values between -1 and 1 are excluded because it's impossible for us to get to them. So in order to get values in between -1 and 1, we'd have to take 1 and we'd have to divide by something bigger than 1. So for example, 1/2, we'd have 1 divided by 2. Well, sine can never be 2. It can only be between -1 and 1. And similarly for negative fractions, we can't have -2 equals sine. Because the range restriction of sine and cosine, this actually restricts the range of secant and cosecant so that even though we're including all of those values above 1 and below -1, all the values in between are impossible to attain. Because again, to reach values when we take 1 and divide by sine, to get values that are in between 1 and -1, we'd have to get sine to output a value bigger than 1 or bigger than -1. And since that's not in the range of sine or cosine, we can't attain those values.